Hey everybody, hope you're doing well. Welcome to the start of week 6 of the fourth marking period here in CP Algebra 2. You'll notice we have finally moved out of Unit 8 and we are into Unit 9, which is going to deal with the topic of sequences and series. So we're going to move away from all the stuff with logarithms and exponential functions. We're going to do something here that's a little bit different, a little less complicated in terms of its algebra, but obviously it has its own components in setting up and solving these different things. So this video here is going to walk you through the basics as to what a sequence is in general, and then we're going to talk about specifically what an arithmetic sequence is. This chapter here, we're going to talk about two different types of sequences and two different types of series. It's a much shorter chapter, obviously, because we're running out of time here in the school year, but we only got about 4 topics here with this particular unit. So, first of 4 here, let's talk about arithmetic sequences. First and foremost here, a sequence in general is kind of like, in essence, a specific pattern. So what we're going to look at here first, before we get into what an arithmetic sequence is, let's find some basic patterns. Let's go ahead and find some extra terms here. So at the top of the screen here, you'll notice there are 4 sets of sequences here. Give you the first 4 terms in each. What we're going to do is figure out what the pattern is from one number to the next, and then we'll fill in the blanks, go find the next handful of terms. So if you can figure out the patterns here, feel free, fill them in, fill in the next term, see if what you get matches what I have. So let's look at the first one. First one, we got 1, 5, 9, 13. If I look from the first number to the next, 1 to 5, I could add 4 or multiply by 5. Those would probably be the 2 most logical choices there. Take those patterns and see, okay, well, how do I get from 5 to 9? Well, I can add by 4 and continue that pattern. 9 to 13, I can add by 4, continue the pattern. So I would say to establish this pattern, we'd add 4 from one number to the next. So if I do that, 17, 21, and 25 would be the next 3 numbers in my sequence. Number 2, negative 5, 10, negative 20, 40, blank, blank, blank. Most logical pattern for that, based on the numbers given, is to multiply by negative 2. So negative 5 times negative 2 is 10, times negative 2 gets you negative 20, times that is 40, multiply that by negative 2, 80, positive 160, negative 320. The next pattern that we have here, 3, 7, 15, 31. Now this one's a little bit trickier to figure out, but if we look from 3 to 7, the most logical thing to do would be to add 4. But obviously, if I add 4 to 7, I'm not getting 15. And then if I add 4 to 15, I'm not getting 31. This pattern here has more of a progression to it, where if I go from 3 to 7, I add 4. 7 to 15, adding 8. 15 to 31, I add 16. So you'll notice here, each time I'm adding, I'm doubling what I previously added. So my pattern here might be a little weird to put into words here, but basically my pattern is this. Add 4. The next time I'm adding, I'm doubling what I just added, so I'm going to add 8. Then I double it again to add 16, which then means to get my next number, I'd add 32. Then I'd add 64. Then I'd add 128. So basically all powers of 2. So I'm going to add 32 to the 31, get the next term 63. Then add, again, double 32, 64. To the 63, I'm going to get 127. And then I'm going to add 128 to that and get 255. The sequences we'll be dealing with here aren't going to have that complicated necessarily of a pattern to them. We're going to see a lot more sequencing like numbers 1 and 2. But again, it's just another pattern to establish. Last one here, number 4, 1, 8, 27, 64. These are actually your perfect cubes. The first term is 1 cubed. The second term, 2 cubed. The third term, 3 cubed. The fourth term, 4 cubed. So the pattern is the number of the term cubed. Okay, so the positioning of the term in the sequence, you cube that, and that's how you get your result. So the fifth term would be 5 cubed, 125. The sixth term would be 6 cubed, 216. The seventh term would be 7 cubed, 343. So again, just looking at the basics of establishing patterns, and again, we're going to look at more specific types here, more similar to what we see in numbers 1 and 2. Now, with patterns, especially when they're not as maybe explicit as at least the first couple of examples, we can write equations or rules. Okay, you're going to see both those words interchanged in most cases that allow us to find all the terms of a sequence. Okay, so a sequence has a domain that is a consecutive set of integers, and again, it follows a specific pattern in some sort of way. There are two types of sequences, finite and infinite. This is just more for knowledge when you see these words. A finite sequence just has a limited number of terms, so you can see 2, 4, 6, 8, 10. It stops. For infinite, it has an unlimited number of terms. The way that you'll know if something is infinite is right here with these dot, dot, dots. If you see a list of numbers and then you see dot, dot, dot after it, that means technically it is going on infinitely. That will come into play in one or two details here throughout the chapter, but it's not something that is going to be overly prevalent, but it's just something, again, you're going to see that term. I want you to know what that means and how you know if something is infinite or not. Now, before we get into the specific type of arithmetic sequences here, let's talk about here how we use an equation to find terms. So, we're going to use the rules below to find the first 5 terms of the sequence. So, first one here has a sub n equals 5n plus 11. Typically in these problems, n represents the number of the term, the position of the term in the sequence. So if I want to find the first term, I'm going to plug 1 in for n. Okay, so you see that a sub 1, that's a fancy way of saying first term. So you do some quick PEMDAS, the first term would be 16. If I want to know the second term, I plug in 2 for n. Do some quick PEMDAS, you get 21. So on and so forth. If I want the third term, plug in the 3. Fourth term, plug in the 4. And the fifth term, plug in the 5. So you can see the math behind it isn't that complex, but ultimately it's just knowing what the variables stand for. So you can see the first 5 terms, 16, 21, 26, 31, 36. Same idea in the second example. If I want the first 5 terms, again, I'm going to plug in 1 through 5 for n. So if I want the first term, that's a sub 1. And again, just making sure we do some good PEMDAS here. We get 3. Second term, plug in the 2. Third term, plug in the 3. Fourth term, plug in 4. And fifth term, plug in the 5. So again, quick PEMDAS here, plug it in your calculator, do it in your head. You get answers of 3, 12, 27, 48, and 75. So, as we go through this here, okay, you'll notice that we'll be finding terms for different, as part of these different sequences. We're not going to go through and be plugging and chugging to find an infinite amount of terms. That would be an inefficient process. What we're going to take a look at now is how can we use different setups or patterns, etc., to use different types of sequences to write equations so that we can more quickly find terms and find the information that we're looking for. So, on the next screen here, let's talk about the first of the 2 major types of sequences we are going to go through. We're going to talk about, again, the arithmetic sequence. So what an arithmetic sequence is a sequence that has a common difference amongst all terms. And what a common difference is a consistent value that is added or subtracted from one term to the next. So I know we see that word difference, we typically think subtraction. Again, subtraction and addition are similar operations to one another, and the fact that they're just inverses of one another. So we're looking for something that's being consistently added or subtracted with our patterns in order for something to be arithmetic. So these first couple of examples here, all we're going to do is determine if they are arithmetic sequences. So all I'm looking for is the same thing being added or subtracted for all of the numbers that are given. So if I look at number 1, given my sequence, this is arithmetic. The reason being is every time I go from one number to the next, I'm adding 2. So the fact that every time I'm adding 2 to get my next number, we would say, yes, this is arithmetic. The common difference is positive 2. If I look at the second example, I would say this is not an arithmetic sequence because looking from one number to the next. To get from 32 to 37, I'd have to add 5. Well, the next set of numbers, I'd have to add 10, then 20, then 40. It is a pattern, but it is not this specific arithmetic pattern. So this is not considered an arithmetic sequence. Same thing here in number 3. I can add 2 to the first, between the first two terms, but then I'd have to add 4 to get from 4 to 8, add 8 to get 8 to 16, add 16, etc. Again, it does have a nice little patterning ring to it, but we're not adding the same thing every single time. So what we're going to be looking at are sequences here where the same thing is being added or subtracted all the way throughout. So let's talk about how to come up with rules, how to come up with equations when we have a sequence where everything is consistent in a pattern that's being added or subtracted by the same thing every single time. So you can see here at the top of this next screen here, the rule to find an arithmetic sequence, to write it I should say. A sub n equals a sub 1 plus the product of n minus 1 times d. What does that all mean? All the variables here are laid out for you. A sub 1 is the value of the first term. D is the common difference. N is the position of the term in the sequence. So if it's the first term, you plug 1 in for n. Second term, plug 2 in for n, etc. A sub n is the value of whatever the nth term is in the sequence. So if I tell you a sub 9 is 37, that means the ninth term is 37. You would plug in 37 for that a sub n slot. So we'll see how we're going to use those terms in a bunch of different places here. So to write and use a rule for an arithmetic sequence, you're going to follow 3 steps. First and foremost, you're going to identify the first term, so the a sub 1, and find the common difference. The patterns you should be given, they should be pretty easy to hopefully spot. Second step is you'll substitute them into the formula and simplify. So you are not going to necessarily get, you're not getting a final answer, you're getting an equation that would represent to find all the terms humanly possible. If you're then asked to use a rule to find an nth term, so a sub n, so if you're asked to find a 20th term, a 40th term, whatever the case may be, substitute that in for n, and you go solve. So 3 examples here underneath. They are arithmetic sequences, so we're going to go ahead, identify the pieces we need, plug them into the formula, and go from there. Once we do that, we'll use the rule to find a sub 19, which again means we're going to go find the 19th term. So, look at the first example here, 2, 9, 16, 23. First thing I'm going to do, identify my 2 key pieces. What's the first term, and what's the common difference? The first term is 2. That should be pretty easy to spot. The common difference, I'm adding 7 every single time to get from one number to the next. So I'm just going to put those 2 values down so I have them handy. Now, I'm going to go ahead and write the formula. So again, a sub n equals a sub 1 plus n minus 1 times d. Now, if you'll notice, again, the reason why I put the variable d on the right side, you'll see this in a lot of textbooks and stuff like that, has on that side. I have a feeling it's more to prevent you from making very bad order of operations mistakes, so you don't accidentally add the first term of the difference together by accident when you shouldn't be doing that. Here's your formula. Let's go ahead and plug in what we know. So, plug in a sub 1, plug in d. So now remember, the d is connected by multiplication. So we're going to simplify this by distributing the 7 to the n minus 1. So that'll give me a sub n equals 2 plus 7n minus 7. We'll simplify that by combining like terms, the 2 and the negative 7. And I'll have a final formula of 7n minus 5. So that's going to be my rule for the arithmetic sequence. That right there will represent all the possible solutions that I can get based on whatever term I'm trying to find. So now the second piece of it is to use the rule to find the 19th term, a sub 19. Okay, so one other thing I can write down here, and actually I'll write this a little bit lower, because ultimately we don't want to use, don't want to use that n value of 19 until we actually have an equation that's written down. So what I'm going to do now is break this off a little. We're going to go find A19. So that means the n value is 19. So I'm going to go back to my formula, plug in 19 anywhere I see an n. Now, A sub 19, you're not actually finding A, okay? That is just a way, again, that we write it. So it's just notation. All I'm going to do is all the math on the right. So 7 times 19 is 133 minus 5 is 128. So what this means, if I were to put it in words, and you don't necessarily have to do this, but A sub 19 equals 128 is just a fancy way of saying the 19th term is 128. And that's how you go ahead and write a rule and go find a specified term. So in the next two examples here, we're going to go ahead and repeat that process. So let's go ahead and do so. So number 2, we're going to identify again first term, common difference. So the first term is 57. Common difference, you have to subtract by 12 to get from one number to the next. So my difference is negative 12. So let's go ahead and write out our formula. Let's plug in, again, first term here, that A1 and D. So again, I'm going to distribute the value for D. It's being multiplied to the n minus 1. Distribute that in. So I'll get 57 minus 12n plus 12. Just watch your signs. Don't make any goofy algebra mistakes there. Combine your like terms. Your 57 and 12. You'll get negative 12n plus 69. That'll be your rule. Now we'll go ahead and find the 19th term. So again, that means n is 19. So I plug in the 19 where I see the value for, the variable n. So again, all I'm going to do is negative 12 times 19, which is negative 228, plus 69. The 19th term is negative 159. And in number 3, same idea. Our first term is negative 30. Our common difference, we have to add 10 each time. So D equals positive 10. So again, we're going to go ahead. Now, I'm writing out the formula every single time. Obviously, you could just keep it handy and not have to write it every single time. Whatever works for you is fine with me. Plug in A1. Plug in D. We're going to distribute that 10. So I'll have negative 30 plus 10n minus 10. Combine your like terms, and you'll have a sub n equals 10n minus 40. Now we'll go ahead and find the 19th term. So again, n is 19. So a sub 19 equals 10 times 19 minus 40. 10 times 19 is 190 minus 40. Means the 19th term of the sequence is 150. So that's how you go ahead. If I give you an arithmetic sequence, that's the process you're going to follow. Identify the first term, identify the difference, plug them in, write your formula. Most of the time, you'll be asked to follow up and then use the formula to go find a specific term, well, then do so. Plug in that value for the n, and go ahead and do some quick solving using your calculator. The last part of this I'm going to show you here is how to write a rule if you're given, instead of the first term, you're given some other random term in the sequence and the common difference. So you notice at the top of the screen I have the formula handy once again. We're still going to use the same formula for this. To do this, it's just a matter of, in order to write a formula for a sequence, you need to know the first term and the difference. If I don't give you the first term, we have to go find it. So the way that we're going to do that, step 1, plug in that nth term for a sub n, the n value, and the common difference into the formula. We'll use it to solve to find the value of the first term, the a sub 1. and then we'll go ahead and write the rule like we did in the last three examples using that new a sub 1 term, that first term that we found, and the common difference, and we'll simplify that as we need to. Once we get the rule in this case, I'm not going to have you go find another term after it because, again, theoretically I could, but there's enough work to be done just to get to the rule in this situation. So let's go ahead and walk through these couple of examples and see what we come up with. So here in number 1, I tell you a sub 11. So the 11th term is 41. The common difference, d equals 5. So let's identify a couple of things real quick. We know for the a sub n, we're plugging in 41 because, again, I'm telling you an nth term. I'm telling you the 11th term is 41. We're going to plug that in. The n value is 11, okay, and that comes from the little subscript there. And we know d equals 5. That's explicitly given to us. So I'm going to go ahead and write out our formula. And let's plug in what we know. So again, 41 goes into the a sub n spot because we actually know what that is. We don't know a sub 1. That's what we're trying to find. We know we're given the 11th term and that the common difference is 5. So now it's just a matter of, again, you could probably do this in a couple less steps PEMDAS wise, but that's just, again, your personal preference. We know in parentheses this becomes 11 minus 1 is 10. We multiply the 10 and the 5 together. That gets 50. Get a sub 1 by itself by subtracting 50. Negative 9 is a sub 1. So what that means, the first term is negative 9. So when it comes to writing the rule, so again, we're going to use our format. To write the main rule, we need the first term, so that negative 9. And we need the common difference, 5. So once again, I'm going to set this up just like we did last time, or the last three examples. So again, I distribute that 5 to the n minus 1. Combine my like terms. I get a final rule of 5n minus 14. So again, it's a little bit of a process. It's not exactly the quickest thing to do, but the algebra behind it is far less complex than what you've been doing. So hopefully you don't find that aspect difficult. It's just a matter of, again, just like anything else, identifying what pieces you have and working through them. Last example here in number 2, same exact idea. I give you the 26th term and the common difference. So we know the nth term that's randomly given to us is negative 238. We know n is 26 based on the subscript, and we know the common difference is negative 12. So once again, I'm going to take those pieces, plug them into my formula, then I'm going to write out for the 8 billionth time. So I'll have negative 238 equals a sub 1 plus the product of 26 minus 1 times negative 12. So in parentheses, this will become 25 times negative 12. 25 times negative 12 is negative 300. I'd add 300 to both sides, telling me that 62 is a sub 1. So the first term of the sequence would be 62. And now that I have that, I'm going to go ahead and write the actual rule. So again, if I'm writing the actual rule, I just plug in a sub 1 and d. So I simplify. So I'd have 62 minus 12n plus 12. Combine my like terms. My final rule would be negative 12n plus 74. So that's how you work with arithmetic sequences. You're going to see a lot of the same processes in the most of the lessons here for this chapter, because you're going to see a lot of rule writing. The next video we're going to talk about what are called geometric sequences and kind of work through the same steps here. So this will get a little bit easier for sure as we continue throughout this unit, because all of this really builds and stacks on top of each other. So make sure to complete the graded assignment that goes with this. I believe it's 6 questions, so shouldn't be anything too complex. or take hopefully too long. It's basically 2 problems of each of the sets that I showed you here in this video. So thanks for watching. I know this one was a little bit longer, but this will really help you out as we go through the next couple of weeks, and they should be shorter as we move on from here. So as always, if you have any questions, send me an email, send me a message on Schoology, or stop by my office hours on Zoom. I'll be more than happy to help you out with whatever you need. Otherwise, again, thank you for watching. Stay safe, stay healthy, and we'll see you next time.